So, now I will demonstrate how to measure the angle of uh, of a given prism. Okay. So, this is the experiment 1. So, measurement of angle of a given prism. Okay. So, what is the working formula for this? So, see, this is the prism. So, from collimator parallel rays are coming and falling on the prisms. So, prism we have put on the prism table in such a way, this apex, okay, it is uh, towards the collimator, and just base of the prism is just opposite side of the collimator or towards the telescope. Okay. Now, light or parallel light are falling on the prism. So, you can see these two are, this is the base. So, that means this and these two faces are the refracting face, okay, transparent face, or it can reflect also. So, here you can see uh, half of the light will fall on this face and half of the light will fall the other face. Okay. So, light will reflect. So, this ray say is reflected in this direction and this ray will reflect in this direction, right. So, before, so this is the from collimator, if prism is not there. So, this is the direction of the light, direction of the collimator rays. Okay. So, now because of prism it is reflected in this direction, also from this surface in this direction. So, now you just think that this is a reflecting surface. So, if I take out this prism and if I think that the mirror I have put, that is the parallel to the mirror's face, surface is parallel to the incident rays. Okay. So, incident rays will, so basically they will pass in this direction. Now, if I just make an angle rotating this one. So, if I keeping the incident rays fixed, if I rotate mirror by angle theta, okay, so then reflected ray will move by 2 theta, will rotate by 2 theta. So, that is the standard fact we know. If mirror is rotated by angle theta, then reflected ray will rotated by 2 theta. Okay. So, here you see this space, actually if I think that it's from this direction, it's rotated by angle a by 2. If this the angle of the prism is a, so this half angle this is a by 2. So, now this reflecting face is basically from this place, if I think that is rotated by a by 2. Okay. So, then reflected ray, so this ray will be rotated by 2 theta, means a by 2 into 2 by, that means a. Okay. So, similarly other side also. So, this face is it's say from here we can think that is rotated by a by 2. So, reflected ray this ray will rotated by 2 into this angle a by 2. So, so this angle, so angle between these two reflected rays from the two faces, this angle is 2a. Okay. So, if if I measure putting the telescope here, if I measure the angle, if I measure the what is the reading of the telescope, okay, when it is at this position, and then take the telescope in this direction, and what is the reading of the telescope. So, if you take the difference of these two reading, then I will get basically this angle, okay. So, and that is 2a, that is 2a, okay. So, angle of the prism will be then half of it, okay. So, experimentally what we have to do? We have to put the prism on the prism table like this, okay, keeping apex towards the collimators, and opposite to that one is basically base, okay. And then we have to see the reflected ray in this side, put the telescope, take the reading, and take the telescope in other side, find out the reflected rays, and take the reading of the telescope when it is at this position, okay, and then we can find out the angle of the prism. So, this is the experiment, okay. So, before doing measurement, let me tell you few things. So, this is the spectrometer I have showed you, right. So, this is the base, basically this is the base, and this base on three leveling screw, okay, and this telescope is fixed with this base, okay. So, basically collimator is fixed. So, this base we cannot rotate, move, okay. So, telescope is fixed with this base. So, telescope is fixed. So, telescope will not rotate the telescope, okay. So, that means in telescope what is there? Sorry, not telescope, collimator. So, collimator is fixed, it is attached with the base, okay. So, that means this collimator, in collimator what is there? We have slit here, slit source, okay, and from slit source light are coming, falling on the lens, and parallel rays are coming. So, this collimator is fixed means incident this rays are coming from the collimator and falling on the prism. So, this rays, incoming rays are fixed, we cannot rotate. So, that is why slit source or rays are attached with the collimator, that is fixed, okay. Vernier scale attached with the prism table. So, this is the prism table, okay, this is the prism table, and prism table height we can adjust using this tightening or losing this one, okay. Now, this prism table is basically attached with this vernier base, okay. So, basically vernier is attached with this prism table. So, that is what. So, that means if I rotate the prism table, so basically vernier will rotate. So, reading will change, that I will tell you in details. And then this telescope is attached with the main scale, main circular scale. So, if telescope rotate, that means reading will change. If prism table rotates, vernier rotates, then reading will change, okay. So, for the experiment, sometimes I need the provision to change the prism, to rotate the prism table without rotating the vernier. So, in that case actually, so there is a provision here. So, this we have to fix it, clamp it, and then we can rotate it. So, in this case you see vernier is not attaching. So, when I am rotating this one vernier, so then this table also rotating. Now, if I just without changing the vernier, that means without changing the reading, I have provision to change the prism table. That means I can change the angle of the incident ray, okay, etc., etc. So, this is very important during measurement. Okay. So, without changing the reading, I can change the angle of incident ray on the prism. Okay. So, if I change this one, reading will change because vernier is moving. If I change the position of the telescope, we can change the reading. Okay. So, reading can change due to either or both rotation of the prism table and or telescope, right. So, here prism table means I mean this one. Okay. So, but notice the facts in the scale. If I open this one, so this is the circular scale, right. So, in this circular scale, so 0 to 360 degree angles are there, 0 to 360 degree angles are there, right. So, 0 and 360 degree are at the same position on the scale, they are on the same position. Also, there are two verniers, vernier 1 and vernier 2 other side. Okay. These two verniers are basically, they difference in reading of vernier 1 and vernier 2 is always 180 degree. Okay. There, so angle is 180 degree. Okay. So, third one is calculation of angle is the difference in reading of vernier 1 in two positions, not of vernier 1 and vernier 2 reading. Okay. So, calculation of angle with how much it is rotated. Okay. So, if I want to find out, so actually we have to take, so for this position what is the reading of vernier 1, what is the reading of vernier 2. Okay. So, now I rotate it. Now, what is the reading of vernier 1, what is the reading of vernier 2. So, now this angle of rotation, if I want to find out, so that is basically difference of two reading of vernier 1. Okay. Also, the same difference you should get from the difference of two reading from vernier 2. Okay. So, these two always separately we use. Okay. We never mixed, we never subtract or add reading of vernier 1 and vernier 2, whatever the subtraction, addition, whatever. So, this for vernier 1 and separately for vernier 2. Okay. And when you will take this reading for a particular, for this position, say suppose this reading is 40 and other one is how much it will be. See, if some student tells, sir, it is 110, 210. So, it is wrong basically. Okay. So, if you remember that they are at 180, their difference is 180. So, if it is 40, so it will be 180 plus 40, 220. Okay. So, it may not be exactly 220, but it will be close to the 220. So, always one should cross verify when you are taking reading. So, there should not be major mistake in taking reading. Okay. Next, another thing I would like to discuss, this ambiguity. during taking reading or during calculation of the reading. Okay. So, this also generally we do mistake. So, this is the main scale, circular scale. So, 0 and 360° basically same point. Okay. So, if it is 0 or 360, then it is 180, this say this 90 and this is 270, and in between 1, 2, 3, 4 etc. So, here so this marking is 0, 10, 20, 30, 40 like this. Okay. Now, so this is the vernier position. If this is the vernier position, okay, one vernier reading is 40. Okay. So, something like this. Okay. So, one reading of the vernier is say vernier 1, C is 40, and vernier 2, if I see this reading is 220°. Okay. So, this is the initial position. I have noted down the reading. So, I may need to rotate it clockwise or I may need to rotate it anti-clockwise, depending on my experiment, depending on my demand. Okay. So, if I rotate it clockwise by 50°, say a telescope is rotated by 50° approximately. So, if I rotate it, it is the clockwise means this way. Okay. If I rotated it by say 50°, what will be the reading of the vernier? If you see the reading of the vernier, so what I have rotated? I have rotated, so vernier that is constant. This part is constant, keeping constant. I am not rotating the prism table. Okay. So, this part remains this same position. So, actually I rotate the, I have telescope means I have rotated the main scale, main circular scale by 50°. That means here 40, then more 50 is rotated. So, this 90 will come at this position, vernier 1. 90 will come at this vernier position, and 270, that reading will come at vernier 2. So, reading will be basically, if you see the reading, so you will see this reading, you will see this 90°, and this reading is 270°. Okay. So, fine, because then as I told, we have to take difference of this two reading of the vernier 1. Two reading of the vernier 90° minus 40° equal to 50°, and you can take that difference of two reading of the vernier 2. So, vernier 2 270° minus 220 50°. Okay. So, basically this rotation I have given 50°. Okay, as I just told. So, from calculation you will get 50° from both, and then take generally it is exactly not 50°, it is 49°, 59 minute, say 45 second. So, using the vernier constant one can find out. So, then reading or angle of rotation whatever from vernier 1 you will get and vernier 2 you will get, then we will take the average of these two readings. You come back to this original position, when again this position vernier at reading is 40° and other one is 220°. Okay. Now, you rotate it anti-clockwise by 50° again, you rotate it anti-clockwise by 50° again. So, anti-clockwise, so I will rotate it anti-clockwise approximately by 50°. Okay. So, again this vernier are fixed, we have not touched this table. Okay. So, reading will change, either you change the telescope position or you change the vernier this prism table position. Okay. So, we have kept the prism table position fixed means vernier fixed. Okay. So, when rotated by anti-clockwise, so main scale is rotated by 50 degree. Okay. So, what will happen? So, this part will come at this vernier position, at this vernier position. Okay. So, this reading, what is this? 1, 2, 3 up to this, these are 350 and then 360. So, here this side, this part has come below the vernier. So, reading say it is 350 degree. Okay, it will show 350 degree, and the other side it will, so this will go here anti-clockwise. I have rotated 170. So, vernier 2 it is giving reading 170 and this reading is 350 degree. Okay. Now, so difference between these two reading, of vernier 1, what is the difference? 350 degree minus 40, it is 310 degree. Okay. And difference of these two reading, 220 minus 170, 220 minus 170 or whatever. Okay. So, 170, difference between 170 and 220, that is 50 degree. Okay. So, I mentioned that I rotated it to approximately 50. So, this vernier 2 it is giving me this rotation, this reading result I am getting 50 degree, but vernier 1 is telling me no, this angle of rotation, this whatever rotation, it is 310 degree, but it is impossible. This both has to be same, approximately same. There may be difference in second or in minutes. Okay. So, what is the ambiguity? Here look. So, when I am rotating it is anti-clockwise, that means that 0. So, when 0 is coming here, so that means it's already it is rotated by 40 degree, and then so it's rotated more 10 degree. So, then this reading is coming 350. Okay. So, this basically 40 degree and this it's so this rotation is extra 10 degree. So, how we find out this 10 degree? So, basically 360 degree minus 350. In such case, you have to take 40 plus this reading is not 0, this 360 degree minus this 350 degree, that is basically 10. So, 40 plus 10 equal to 50. So, calculation for this vernier 1, we have to do like this: 40 degree plus 360 minus 350 degree, so equal to 50 degree. Okay. So, that is the ambiguity. So, one has to be very careful during calculation. Okay. So, now let us do the experiment, record the data. So, we have to record experimental data. Okay, recording. So, first task is to find out the least count of the spectrometers. Okay. That means vernier constant of the two verniers. Okay. So, vernier 1 and vernier 2. So, what I have to see? How many divisions? So, from here I have to see how many divisions are there. I can see 0, 10, 20, 30, 40, 50, 60. 60 divisions are there. We have to note down vernier 1, number of vernier scale division equal to 60, smallest division. Okay. Vernier 2 also is 60. Both are basically having same vernier constant. Now, one has to find out main scale. What is the smallest division in main scale? So, you have to see, you have to find out for your spectrometer. In our spectrometer, 1 degree, between 1 degree there are 3 division So, one division is basically 1/3 degree. Okay. So, smallest division in main scale equal to 1/3 degree, or 1 degree, you know, this 60 minute. So, it is a 20 minute. Okay. So, Vernier constant is basically one main scale division divided by total Vernier scale division. So, if you calculate, so it is a 20 second. So, for both Vernier, the Vernier constant is 20 second, that one has to find out first. Okay. Then set the experiment, as I showed how to set the experiment, as I showed you that this is the geometry of the experiment. Okay. So, this is the base, this is the apex. So, it will be towards the collimator, this is my prism. So, this is the apex, this is the apex. Okay. So, this is basically prism angle. So, here we have taken sodium source, it is a single wavelength sodium D line, okay, yellow color. So, its wavelength is 5893 most probably angstrom, 5893 angstrom. So, so this spectrometer is leveled and also it is focused for parallel rays. Okay. How to do that, that I explained. Okay. So, one has to do that using the spirit level, putting here, adjusting this, etc., etc. So, I will not repeat that one. So, now I have to, so this is the base, just opposite to I will put this way, I will put this way. So, generally, yes, this way you can put. So, here initially what, so these two Vernier scale you should keep in this position, so that you can take the reading easily in both sides. Okay. So, now this one approximately I will put apex is towards the collimator and that base is other side. Okay. So, then what you should do, so you should just look, so there will be reflection from this face and there will be reflection from the other face. Okay. So, with bare eye you can just approximately see, okay, I can see here the reflected one. So, then I will, so what I have to do now, I will clamp the prism table. Okay. I clamp the prism table, so this Vernier will not change the position, will not rotate. Okay. So, whatever the change of reading, it will come due to the telescope. So, telescope I will take in this position, yeah. So, approximately I have taken the at the position of the reflected rays. So, now I will just tighten this part. So, I should tighten this one, but here there is a obstacle anyway. So, using the basically this screw, one can just change the crosswire, position of the crosswire, and make it coincide with the line. Okay, spectral line. So, one should do that, and okay. So, say it is at this position, crosswire is aligned, or here this cross position basically I put on the line. It's like this. This is the line and this is the crosswire. Okay, this way I have put. Now I have to take the reading of Vernier 1, okay, and then one should take the reading of Vernier 2. Okay. So, then you need table, data, table for recording the data. So, this is the table. So, from the table what you have to measure you can understand. So, here this column is vernier number. So, I have two vernier, vernier 1 and vernier 2. The number of observation means in vernier 1, okay. So, we will measure 3 times, okay, and at the same time this for vernier 2 simultaneously we will get this reading. Okay. So, reading at the first position of the telescope, at the first position of the telescope, reading at the second position of the telescope means if I take this is the first position of the telescope, okay, for this position I will note down the reading of vernier 1, note down the reading of vernier 1, what is the main scale reading, okay, main scale reading, and then this just simply slide calipers, you know. The way you have taken reading from slide caliper same way. So, main scale reading, then vernier scale reading, okay. Here this vernier constant you know this 20 second, okay. So, including that one, so one can write this vernier reading. So, then total reading is basically this m plus v, okay. Then you can just disturb it, again come back here, then take the second reading. So, for vernier 1 here you have taken reading, and then for vernier 2 you have taken reading. So, just you disturb it and come back again, take second set reading, then third set reading, okay. So, this just to minimize the error, experimental error, we take generally not a one data, but more than one data. So, basically here you will take reading for the first position of the telescope. I have to see, yes, I can see, and then take the telescope in this position. Yes, I got it. Actually, I have to tighten it. Yes, I can tighten it, and then I can use this fine screw to move it, okay, to align this one. Now, take the reading, taking reading in same way for the second position, okay, for the second position of the telescope, okay. You take the reading from vernier 1, okay, observation number 1, then for vernier 2, observation number 1, take reading, and then again you disturb and come back again, okay, or just you try to align properly, try to get more accurate, okay, and then again take reading. So, this way 3 times we take reading for both from both vernier, okay. Now, here if this is theta 1 and this is theta 2, so from each setting, so you will get for observation number 1, so you will get theta 1 minus theta 2. For observation number 2, 3, you will get 3 data here. Here also you will get 3 data, okay. They should be more or less approximately same, okay. So, there may be difference or there may be mistaking taking reading. So, that is why now basically we have 6 data, okay. Now, take average of the 6 data, that will be the mean 2A. So, whatever reading we are getting, okay, here. So, that I mentioned that is basically 2A. So, you will get 2A. Now, angle of the prism you can calculate mean 2A whatever you get divided by 2, that is equal to A, okay. So, this experiment is very simple and nice, okay. Important fact is that, so you have to be habituated with the labeling of the spectrometer and with the Schuster's method or other ones other method I mentioned that if you focus the telescope in distant object. That way also you can get the parallel, you can get the condition for parallel rays. Okay, so after that you have to understand the theory, geometry of the experiment whatever you are going to do, and according to that geometry you just do the experiment, take the reading properly, okay, and calculate. So here I demonstrate how to measure the angle of prism. Okay, so I'll stop here. Thank you for your attention.